So now we are going to learn about basics of Z transforms, which is important for what we are supposed to learn in our third and your later modules. So we look into the basic concepts of those things. So we have already looked into what a transform is, and we have already learned many aspects of it. So we have already looked into different kinds of transforms, and transforms, as we know, it converts a signal that exists in one domain to another. So we had already looked into CTFT, we have already looked into DTFT, and we have looked into DFT also. So all these transforms, they converted signals which existed in time domain to the frequency domain. With this one is characterized by CTFT. X of n was characterized, which is a discrete version, into x of omega. That was the job of DTFT. And DFT, x of n got converted. That is, a discrete time signal got converted to a discrete frequency signal. Along with this, we had looked into another one transform, that was Laplace transform, where your time domain signal got converted to your S domain. So x of t got converted to x of s. Similarly, we are going to learn about Z transforms right now. So your Z transform basically again deals with conversion of x of t, or rather x of n, to x of z. That means a signal existing in time domain, it will be converted to the z domain. Now how do we do this? Now we have got a simple formula to implement this particular thing. That is, x of z is equal to summation n equal to minus infinity to infinity x of n z raised to minus n. So this is a formula that is to be learned, and through which we'll be doing many problems. So this is simply the formula for Z transform. So if we are to look at an example, so if I give you a signal like, or a question like, find x of z where x of n is 1, 2, 3, 4. Now in this particular question, the position of n is not specified, so we can basically take it as beginning from 0. So your n will be lying from 0 to 3. So this is the x of n signal, that is starting from 0, 1, 2 and 3. So the amplitude values are 1, 2, 3, 4, and the position values will be 0 to 3. So if you are to solve this particular thing, or if you are supposed to find out x of z, what we are supposed to do is implement this particular formula. So getting on with it, x of z will be equal to summation n equal to minus infinity to infinity x of n z raised to minus n. So as we know over here in this particular question, your n lies from 0 to 3, so n will be equal to 0 to 3 x of n z raised to minus n. So that will be like x of 0 into z raised to minus 0 plus x of 1 z raised to minus 1 plus x of 2 z raised to minus 2 plus x of 3 z raised to minus 3. So substituting this, x of 0 will be like 1, and z raised to 0 is already 1, so it can remain like that. X of 1 is 2 z raised to minus 1 plus 3 z raised to minus 2 plus 4 z raised to minus 3. So this is x of z of that particular signal. Now if we look at it in a different perspective, like I give it another question where you have to find out x of z for x of n, that is 3, 2, 1, 2, 3, where arrow comes under here. So this would mean this arrow would represent the position 0. So your n will be ranging from minus 2 to plus 2 over here. So when we look at this particular thing, x of k, it can be written as summation of n equal to minus 2 to 2 x of n z raised to minus n. So that would mean x of minus 2 into z raised to minus of minus 2 plus x of minus 1 z raised to minus of minus 1 plus x of 0 into z raised to minus 0 plus x of 1 z raised to minus 1 plus x of 2 z raised to minus 2. So that would mean when we solve this particular problem, that would mean 3 into z raised to 2 plus 2 into z raised to 1, which will be equal to z, plus 1 plus 2z raised to minus 1 plus 3z raised to minus 2. This is again another way of solving this particular z transform problem. Moving on, we are to learn few concepts that is particularly related to the filter design that we are supposed to do. So basically our third module is dealing with filter design, and we are supposed to look into the filter design right now. So as you already know, a filter is again a subject or a topic that you have been learning in various subjects like circuits or your linear integrated circuits, where you have learned about mostly four different kind of filters, that is the low pass, high pass, band pass, and the band reject or the band stop filters. So you know about these filters, and basically you have done your lab experiments also probably in the previous semester. And what would have happened in those kind of filters, you would definitely know that you would have done a question like this: design a low pass filter with cutoff frequency of 2 kilohertz. So you design a filter, you find out a value for R and C. You would probably be having an equation, um, and you would be finding out the equation of R, value of R and C, and you will be setting up a circuit which can filter the signal. What naturally happens is you will be connecting a signal from the function generator into the circuit. Then you'll be taking its output and you'll be looking at its CRO. This input from this particular function generator will be kept constant in terms of amplitude, and you'll be changing the frequency. And when it passes through the circuit, you will note the graph. So most probably in your labs and or what you would have done is you must have plotted a graph of frequency versus gain, where if it was a low pass filter, you would be getting a graph like this, where this would represent your cutoff frequency, that is 2 kilohertz. So all basically, what does low pass mean? Low pass means that it will pass all the frequencies that are below the defined cutoff frequency. So this is why you do it, and your input will be given, you have it passing through the circuit, and you'll be observing the output at CRO. The input amplitude is kept constant, but the frequency is varied, and you naturally get a waveform at the CRO which you'll be measuring, and you will be plotting the gain versus frequency graph. So you would be getting a graph like this, and you can see from this graph that this is a response for a low pass filter. Similarly, you'll be having an idea about what is a response for high pass, band pass, and band reject. So the main point that I want to convey here is that a filter is basically a system. So it is again like the initial concept that we looked into, where we learned about signals and systems. You learned this particular subject, and this element that we are dealing with, this thing called filter, is basically a system, and it will have an input signal and it will have a output signal. What you did in the previous semesters or learned in the previous semesters, and what you did in the labs or can be classified as analog filters, because it basically uh, processed analog signals that came from the function generators, and you got the output and you have observed it in the CRO and all. But henceforth in this subject, we are basically going to deal with digital signals, and basically what you will be designing will be digital filters. Now, like I mentioned before, you have your input signal over here, which will be x of n, and you will be having your h of n over here, and which will give you a y of n. If you remember, when we had previously explained, x of n is the input and y of n is the output, and how y of n will be generated from x of n will be depending upon h of n. If you remember, I had mentioned h of n as impulse response, and in the previous modules I explained something about impulse response and how or what is basically impulse response. So impulse response is a way in which the system will be responding to the impulses that will be coming in the form of the input signal, and that is what defines your output. Now, why do I say about this is that when we talk about this filter, another important thing that comes into the scenario will be system transfer function. System transfer function. So when we speak about system transfer function, if you ask me what is system transfer function, I will say it is h of z. And if you ask me what is h of z is, I would say it is a z transform of, yes, you are absolutely right, h of n. So a system transfer function h of z will be the z transform of h of n, which is the impulse response. Or if I want to define what it is, I can say it as a ratio of the z transform of the output by z transform of the input, and that will be equal to h of z. So this is a primary concept that you have to learn about filters before we move into the actual design.